There is one more trend on the main sequence we can look at, and that's lifetime. Stars spend most of their time on the main sequence. So if we can calculate the time it takes for a star to use up its fuel on the main sequence, this is a good first guess on how long a star will live.
Fortunately, finding a star's main sequence lifetime is fairly easy. It really just depends on two things. How much fuel does it have, and how fast is it using that fuel up? If we look at this in terms of energy, then the rate at which a star is using its fuel is simply the luminosity. So a very luminous star, like an O or B main sequence star, is using fuel much faster than a smaller, less luminous star like the Sun. On the next slide, we'll look at how much fuel a star has.
Remember that main sequence stars get their energy from fusing hydrogen to helium in their cores. Back in the chapter on the Sun, we said that when hydrogen fuses into helium, about 0.7% of the mass, that's about 7 parts in 1,000, disappears. It's turned into energy via the mass-energy formula, E equals mc squared. The other 99.3% is turned into helium.
The hydrogen in a star's core is about 10% of the total mass of the star. So we know that only 10% of the star's mass is available for fusion. Over the main sequence lifetime, the total amount of energy available for fusion is the mass of the star times 10%, because that's how much is in the core, times 0.7%, because that's how much of the hydrogen is turned into energy.
So this tells us the total amount of energy a star can generate while it's on the main sequence. Next, we'll put the pieces together and see how long a star can last on the main sequence.
A star's main sequence lifetime is the time it takes to use up the fuel in its core. We know how much fuel it has and how fast it's using fuel. So the time it would take is simply the amount of fuel divided by the rate it's using up the fuel.
We just saw that the amount of fuel depends on the mass of the star. The rate it's using the fuel is simply the luminosity. So here's the main sequence lifetime of a star. Notice that the only things specific to a particular star that go into this equation are the mass and the luminosity. Everything else is a constant.
Also, this only applies to main sequence stars. If you try this calculation for other kinds of stars, you'll get the wrong answer because they're generating energy in different ways.
Let's look at an example of how we calculate the lifetime of a star. We'll do this calculation for the Sun, a star with a mass of 1 solar mass and a luminosity of 1 solar luminosity. First, we set up the formula. Then we put in the values for the luminosity and the mass. Note that the mass has to be given in kilograms and the luminosity has to be given in joules per second. You're probably going to need to make a unit conversion here.
Then we go ahead and calculate out the lifetime. The units will be in seconds. This comes out of the units for luminosity and the speed of light, both of which have seconds in them. So the main sequence lifetime of the Sun is around 3 times 10 to the 17th seconds. Since a year has just over 3 times 10 to the 7th seconds in it, this converts to 10 to the 10th years, or 10 billion years.
So the Sun can last 10 billion years shining roughly the way it is right now. Geological evidence shows that our solar system is just under 5 billion years old, so our Sun is almost halfway through its main sequence life.
Okay, now you give it a try. See if you can calculate the main sequence lifetime for this star. Also, though, you should check the information given to see if it really is a main sequence star. Do the calculation even if it isn't. It's worth having the practice.
Remember this table? You should be using it to help you keep track of the equations we use in this course. Fill in the main sequence lifetime section of this table now. Keep it and update every time we use a new equation. You'll find this page useful doing homework and reviewing for exams. Depending on your section, you may be required to submit a copy of the completed version for credit. Now we come to the overall trend. Do high-mass stars have longer or shorter lives than low-mass stars? We know that high-mass main-sequence stars are more luminous, so we're really asking which one is more important, the increased mass, and hence the fuel, or the increased luminosity, using up the fuel? It turns out that if you double the mass of a star, the luminosity goes up by much more than 2 times. In fact, luminosity goes up by roughly 8 times when the mass doubles. So changes in luminosity dominate the lifetimes of stars. High-mass stars may have more fuel, but they burn that fuel at a ridiculous rate, so their lives are much shorter. You know what they say? Live fast, die young.
If you look at the HR diagram, you'll see that a 10 solar mass star has a luminosity that is 3,000 times as large as the Sun's. So its lifetime is 300 times smaller than the Sun's, or about 30 million years. On the other hand, a star that has half the Sun's mass is 20 times less luminous, so its main sequence lifetime is 10 times longer than the Sun's, or 100 billion years. Since the age of our universe is only 14 billion years, no stars that small have yet been around long enough to leave the main sequence and turn into giants.
We've mentioned star clusters a couple of times already. A star cluster is a group of stars held close together by gravity. Clusters are an ideal laboratory for studying how stars evolve over time, since all of the stars form close together at about the same time. There are 2 main types of star clusters: open clusters and globular clusters. These form in different ways, in different parts of the galaxy, at different times. We'll look at each in turn, but first I've got a question for you to work on. Open clusters of stars typically have a few hundred to a few thousand stars in them. The most famous example of an open cluster is the Pleiades, or the Seven Sisters. Open clusters are usually less than a few 100 million years old, and some are much younger than this. In fact, many are found in star-forming regions, still surrounded by the clouds they formed out of.
Because of their young age, most of the light from open clusters comes from hot, high-mass main sequence stars. These are the most luminous stars in the cluster, so they're the ones that dominate the light we see. In this picture, there are just a handful of O and B stars that show up well, while the hundreds of fainter main sequence stars are much harder to see. There's a reason open clusters tend to be young. They're only weakly held together by the mutual gravity of the stars. With only a few thousand stars or less, it's easy for stars at the edges of the cluster to drift away, causing the cluster to start to evaporate. The more stars leave, the weaker the overall gravity, so the easier it is for still more stars to leave. Eventually, the entire cluster breaks apart. The stars still exist, but we can no longer recognize them as being from a cluster.
Clusters are most common in and near star-forming regions. It may be that most stars start out in open clusters. Even our sun could have been part of a cluster when it formed billions of years ago. Globular clusters are much larger than open clusters and also much older. They can have hundreds of thousands to over 1 million stars. In most cases, they're 10 to 12 billion years old, making them some of the oldest stars in our galaxy. As we'll see later, most of them may have formed before the disk of our galaxy. The name comes from their shape. They're almost always roughly spherical or globe-shaped. They're bound together for the long term by the gravity of all those stars.
Because of their tremendous age, There are no high-mass stars in globular clusters. All of the high-mass stars have long since died off. Instead, all we see are low-mass stars like the Sun and smaller. Since low-mass main sequence stars aren't very luminous, they don't contribute much light to the cluster. Instead, most of the light comes from a relatively small number of giant stars. Remember, the giants don't necessarily have high mass, just large radii. In fact, these are stars that have recently finished their lives on the main sequence and are now in the late stages of low-mass star evolution. In the next chapter, we'll look at the details of how a star changes after it leaves the main sequence.
I've just been describing the ages of different kinds of clusters, but you might be wondering how we can tell. In fact, there's an easy trick to figure out the age of a cluster of stars. You start by plotting the cluster stars on an HR diagram. This lets you pick out which stars are on the main sequence and which ones are giants. So look at the upper end of the main sequence, where the stars are just beginning to leave the main sequence and move up onto the giant branch. We call this spot the main sequence turnoff.
Next, we calculate the main sequence lifetime of the stars at the main sequence turnoff. We can do this because we know the masses and luminosities of main sequence stars with the given spectral types. In the diagram, this turnoff age is 100 million years.
Lastly, we know that the highest mass, most luminous stars on the main sequence are the next ones that will leave the main sequence, since they have the shortest lives. So the lifetime of these stars must be the age of the cluster. Hence, the age of the cluster is the lifetime of the stars at the main sequence turnoff, 100 million years in this case.